Start my screen share. All right. Can everybody see my screen?
Yep.
Awesome. Put the chat over here. All right. Let me hide this. Does anybody have any questions, any concerns before we get started? Let's see, let's give everybody a couple more minutes to join. How do I stop that ding dong? Can you hear that ding dong when people join?
I think only the host can hear people joining that ding.
Oh, okay. All right. Well, it's really loud. How do they stop you from hearing it? If you can hear my voice, how can you not hear the ding dong? How do they do that? All right, just one more minute. Just waiting for folks to join. Welcome everyone. Wow, it's this is our 4th week, so we'll be about a month into the course already. Time flies. All right, it's 1:35. Let's get started. Let's see. Right, so we are finishing up the 4th week of the semester. We created a database. We learned how to use the UML class diagrams to design a database, right? Graphically, we would had a whole bunch of boxes and arrows, establishing what the structure of the data was. We spent some time on creating it using SQL create statement, creating also tables that were related to one another using foreign keys and primary keys. And this week we've been focusing on retrieving data. You know, if data is stored in the database that has been structured the way we designed it, how is it that you would retrieve data from that database, right? And we talked about relational algebra, and last we met, we started talking about the different syntax of the SQL query. Right? We talked about the select clause, the from clause, the where clause. We're going to wrap that up today and just talk a little bit further other things that you can do with the SQL queries, and we'll finish up with introducing the views. Okay. All right, excellent. So let's finish. Let's review where we left off in the SQL query, right? So real quick, we talked about the select clause, the from clause. We said that it was a mechanism for retrieving data and zeroing in. If you have a whole bunch of tables, then data is spread out over multiple tables with records that are referencing each other. How is it that you can grab all this information that's dispersed from everywhere and just bring it back into one single place? So we saw that the query did that, right? It just filtered a whole bunch of and joined and fetched data from multiple tables and gave you a result set. We looked at the basic queries and renaming and aliases, different shorthands for retrieving all the fields or adding the name of the table in front, just if there was some ambiguity. a couple of examples of the person table and retrieving certain fields. You also distinct so that you would filter out any repetitions. We looked at different data types that fields could be declared as integers, as float, as dates. We saw that we can have lots of function libraries to convert or um, convert different data types, right, or different formats of that same data type. We looked at the date format. String can be concatenated, trimmed, right? That you can calculate substring. You can compare a string against a regular expression, right? We saw the basic patterns for that, and a couple of examples on how you can match certain records to certain values in those fields. We looked at different date functions that and formats that are supported by the various vendors. We saw that there's functions that allow you to do all sorts of arithmetic operations on those dates. So you can add weeks or subtract days, right? Or do the difference between different dates. We saw that different vendors have different formats and different functions available depending on who the vendor is, and you're encouraged to investigate, right, what are the actual functions and formats for that vendor. Um, then, we looked at a couple examples of the select clause where you can do calculations to generate results based on data that is already stored. We looked at a couple examples where we would extract data from a table and we would generate on the fly certain fields that were calculated fields. In this case was the graduating class and the college, right? We saw that we can calculate the value of that resulting field in terms of, data that was already stored in the database. So here was an example. None of this data is permanent, right? This is only for output purpose, right? You are retrieving data from the database. You're massaging that data, adding fields, deciding which fields you want to look at and which order you want to watch, and then they're output and displayed as a tabular format like this. So we looked at an example of starting off with a student ID, name, and graduation year. We started appending new features, new strings, new concatenations, new calculations of concatenating a string, then doing some simple arithmetic to calculate another field, the graduation decade. And we looked at some advanced ways of calculating values using a logical case, as if you had multiple nested if else, or something that looked more like a switch case statement that allow you to calculate the value of a field based on values of the other fields. So here we saw a really trivial example where we are retrieving data from a table, 1, 2, 3, and then outputting the value either the string 1, the string 2, or other. We saw that we can do similar arithmetic with dates to calculate new fields, such as whether you were an alumni or not. And so we calculate how many, in this case, we calculate how many years have you been an alumni, right? And if it's positive, it means that you're an alumni, you've graduated already. Then we going to label you alumni. Otherwise, you're still in the school. We use that. We use this query as a subquery to another query, right? That can then be used with another case statement to spit out whether you were an alumni or you are in school. And we saw that there's a much more terse, compact version of the same statement, but based on the keyword if, right? That can take a predicate that gets evaluated to true, false, and depending on whether it evaluates true, false, it outputs to either the second argument or the third argument based on the value of the first argument, right? We looked at the from clause, right? So we looked at the select clause, then we moved over to the from clause. And here, up to this point, we've been looking at just a single table, right? But as we know, you can combine multiple tables, right? So here's the example. You have student and department. Now, if you select 2, 3, 4 tables without joining or without the where clause, okay, just a from student department or 2 tables, what you get is the cross multiplication of all possible combinations between the 2 tables. okay, which is probably not what you want, right? If you do the cross multiplication between students and departments, right? If you have 9 students, you have 3 departments, you end up with 27 combinations, right? With some fields bringing from the students, some fields coming from the department, and many of these students are not in some of those departments, right? You might have maybe 3 students per department, and so coming out with 29 combinations makes no sense, right? You only want, typically what you want is only those combinations for which there's a relationship between the records, right? That this student is enrolled in that department. You would not want the combination where a student is not enrolled in a department. That combination makes no sense. But if you don't join, if you don't add any joins, or if you don't add any where clause to filter, this is what you would get. You would get all possibilities, all combined, right? Which is what we introduced in the relational algebra. We called it the cross product, right? It was a product of the 2 tables, right, with all possible combinations. We then took a look at something more sensible, right, where you don't really want the product, right? More commonly, what you want is a join, right, where you filter out those combinations that make no sense, right? You don't want to keep the students that are not enrolled in a department. You don't want the combination, right? So typically you combine the 2 tables, right, with an additional statement, which is a predicate, meaning that these are the only ones that I really care, right? Where a student is enrolled in a department. Those I want, right? Everything else I don't want, right? So we do that by adding the join keyword, right? That says, oh, I don't want all of them. I don't want the product. I want a product followed by a select, right? Right. And this is exactly what we're doing, right? We are joining these 2 tables on that specific predicate. Okay. And so here's the syntax is, right, you put the join keyword between the 2 tables, and then at the end you put the predicate. We saw that also, we mentioned that there were more than one type of join, right? The default, the one you're looking at this here, is referred to as the inner join or natural join, okay? And the keyword inner is optional. You don't need to put the inner. No, it's understood that you mean the join, just a regular join, okay? And this is the most common type of join that you'll be dealing day in and day out. But there are a couple more, right? There are the left join, right join, and full outer join, which we covered also. Right. First, we looked at the natural or inner join, right, where we're joining these 2 tables, the orders and persons, and we see that they are some foreign keys of one table are referring to some primary keys in another table. So typically, that's what you do. You join those 2. The foreign key refers to the primary key. It's meaning that you only want the records where there is a relationship between the records from one table and the records from another table. Okay. But we said that there was also the option of bringing in some of those records that didn't have references, right? The ones that have no relationship between the 2. So in this case, we're doing a left join, meaning we're saying, hey, do the join on the predicate, right? So do a regular join, right, between the 2 tables, table 1 and table 2, on this predicate. And so the ones that make sense, the ones that are related. But in addition to that, also bring over those records from the left table, right? There's a left join from the left table that did not have a reference, that were not related. Okay. So here's a case, again, back to the same records that we had earlier. Notice that we're bringing in the last names and first name of the person table, because the person table is on the left. Okay, and notice that there's no matching record on the right-hand side or the order table. We looked at an example where, why would you, we asked ourselves, why would you want to do that? I mean, why would you ever care about those records that are not related to one another? And we saw an example here where, depending on, if you read the requirements of the query, written in plain English, you realize that you also want those fields that are not related, right? In this particular case, right, I want to invite my staff, right, and their spouse if they have a spouse, right? if they don't have a spouse, I still want to invite the staff, right? So this is a very typical example where you want to bring in the additional records that would not necessarily work for an inner join. You have to, in addition, either use a left join or right join, depending on on the ordering of your tables. Right join is basically the opposite of a left join, right? It grabs the data from the right-hand side, like the orders that have no reference, right? And you leave out the ones on the left. We also talked about full join, where you bring in everything basically, right? But in a specific order. You first bring the ones that are related to each other, right? And then you bring in the left, and then you bring in the right, right, of the full join. Okay, let's see. Now and now this is all in good. When you're joining two tables, then it's fairly simple, right? You just say, table 1 join table 2, and then the predicate, right? But it starts getting hard to read, right, when you start joining more than just 2 tables, right? So for instance, here we're joining 3 tables: student with enrollment with section. And so the way you do that is that you have the first join in here, right? You're joining student and enrollment on this predicate. But then the result of that, right, whatever that comes back, right, depending on the records that come back from that join, right, I then want to join again, right? I want to join that on the section, right, on that predicate. Okay, so this can begin to start to look hard to read, right, when you have all this nested parentheses, right? When you're joining 3 tables, 4 tables, 5 tables, right, it becomes really, really hard to read. So an alternative syntax for this would be to instead of using the keyword join, you go back to the cross product syntax, right, where you presumably are generating the cross product, but then you move the predicate that you were joining on, you move it into the where clause. See that? Into the where clause. These two queries are identical, right? They are equivalent to one another, and certainly with the benefit that the syntax down below is slightly easier to read. Okay, it's a little bit easier to read. So we're going to, you can use either one. If it's 2 tables, right, I would encourage you to use the regular join syntax. But if it's more than 2 tables, then certainly this second alternative syntax is much easier to read, and I would encourage you to use that instead. Okay. Now we call this syntax above, we call it the explicit join notation, right? You're explicitly telling me that you're joining these 2 tables, whereas this one, I'm giving you 2 tables, right? And the where clause is basically some generic set of predicates, not necessarily predicates that would necessarily join fields, right? Or that would make a foreign key equal to another primary key. It's just where you can put any filtering predicate, right, of which records you want to keep, right? But if that predicate is based on the quality of one foreign key with a primary key, it's basically implying that you're doing a join, right? So that's why we call it the implicit join notation, right? Where you're not explicitly using the join keyword, but basically that's what you're doing, right? You're joining the 2 tables. Okay, so this, introducing the where clause, right? This is a great segue into the where clause. Let's talk about the where clause. So the where clause is the third and last part of the main select statements. Okay, where you can add predicates on what is it that which record do you actually want to see, right? Up to this point, without the where clause, typically what you get is the entire table, right? You're just saying, well, give me all the table. Well, unless you consider the join, right? The join, didn't retrieve the entire table, right? It joined on several fields, so it's filtering out those parts of the tables that had no relation to other records. right? But the where clause is where you would formally put in any predicates to filter out records that you don't want. Okay, so in the where clause, you can put all sorts of Boolean expressions, right, that it can be combined using and or and not, right, all the Boolean operators, right? And using all sorts of comparisons that you're asking whether something is equal to something else, whether it's bigger, right, whether it's not equal or less than or greater than, blah, blah, blah. So in the where clause, you get to use a lot of the different types of predicate operators, right, where something is greater, not equal. So not equal, notice the not equal symbol, right? So be careful, right? It's not the bang equal, right? It's less than or greater than, right? So that's the symbol that we use for saying that something is not equal. Careful. Also, equal is just a single equal, not an equal like you would use in other programming language. It's a single equal sign, right? You also get some really nifty, pretty cool operators that allow you to consider a range of values, right? Where between allows you to say, is a value within the range of some minimum value and some maximum value, and you can use integers, right, numbers, or you can use also strings, right? Considering that strings are in lexicographical ascending order, right? You can also use like, right, to compute patterns, whether a string value, right, is equal to some pattern. Then you have in, where again you can give an enumerated value set of values by which your field that you're retrieving is going to be compared iteratively against those values, and if it's equal, you want to keep them. Okay. Here are just a couple of really simple examples. Using the select clause to retrieve folks from the city of Lowell. So you get just these two records, right? That is equal to Lowell. You can also combine and make more complex queries based on using the Boolean operators and or not. You can also use parentheses, right, to change the order of operation of the ands and ors. You can, here's an example of using or. Here's a combination of using both and or, and having used the parentheses, right, to combine them and set that you want to do the or before you do the and. Okay. Right. So now oftentimes, in most cases, the what you put in the where clause is predicates that don't deal with foreign keys, primary keys, this foreign key equal to the primary key. Most commonly in the where clause, you put Boolean expressions that are comparing values of non-key fields, right? Like for instance, here we want students that are graduating between 2005 and 2006. Those, graduation year is not a primary key, right, or a foreign key, right? It's just a regular natural key, natural field in the in the student table, right? So that's very, very common, or mostly common, right? Where your predicates are based on non-key fields, but we can absolutely put in there in the where clause. Typically, we can also put in there predicates that are specific to primary key and foreign key, like this one right here. Yes, we're joining together three tables, right? The student with the enrollment, and then the enrollment with the section, right? And we are listing those three tables. So you can use the where clause for both, right? For doing predicates that deal with key fields and predicates that deal with non-key fields, or you can do a combination of both, right? In the where clause, you can have some predicates that deal with filtering based on relationships between one record and another record, whereas you can have other predicates, right, that deal with non-key fields, right? So very much this is doing that, right? It's joining three tables, right? The student, the enrollment, and the section table, right? And then also filtering for specific student, for specific graduation year, and things like that. Okay. Let's see, any questions? Yeah, please don't feel free to interrupt me if I'm losing you, right? But some of this stuff is pretty straightforward, right? So between, as I mentioned earlier, right, it allows you to between and like and in, right? All these operators allow you to consider a range of values, as opposed to saying that it's equal to or greater than a specific value, right? You can now provide a range of values. So between allows you to say, well, is this specific field, right, between these values? Like, for instance, you want to know, give me all the employees who are making anywhere between $70,000 and $80,000, right? And so you would say, give me, a select employee from the employee table where salary between 70 and 80. Okay, and that's going to filter out all the employees that are below 70 or greater than 80, right? You're only keeping that particular value, right? It can be used with integer values or number values, or you can also use it using strings, right? For instance, you can do, give me all the people that are between these two strings, right? And it'll consider strings in alphabetical order. Okay, so Boone and Garcia presumably on an alphabetical order. So here it is. So it returns only these two folks, right? That you get Dole and Garcia being in between Boone and Garcia, right? You can also use the keyword in, right, where you can then enumerate several values by which you want to compare a particular column, right? You say, so-and-so column, I only want the records where this particular column, their value is within these approved valid values, right? If it's anything other than that, something went wrong. I don't want those records. Okay. So here it can be used with integers, and also it can be used with strings, right? So you can say, I don't want the people whose last name is in this predefined set of values. You can also use the functions like or extracting values, right, from a year to transform those data types into primitive data types that can be then compared against, right? So here we're looking at the current year, right, and we want only those students whose name starts with J, right, and are graduating this year, right? So from the current date, right, we're extracting the year, and then we're comparing that year against the student's graduation year, and then we're filtering by that, right? And also using if your name starts with a J. We can also use other tons of these variables, right, that are made available by the database. In particular, current user is tied to the person who is currently logged in. So a professor might have access to this query, and when they run that query, they will get information about their own enrollments, right? If they are teaching that course, then I will show all my students, my enrollments, my section, right? I'm not going to show all of them across the entire university, only the ones about me, right, that I know that I am enrolled. Okay. All right. All right. Any questions there? Everybody good? All right, let's move on then. Let's take a look at subqueries, union, order by, and self joins. Let's talk about that. Okay. Again, same topic all this week, and perhaps next week as well. We'll be talking about queries as well next week. And perhaps we'll get started with SQL programming, which is pretty exciting. All All right, so let's talk about subqueries, right? So all the queries that we've looked at up to this point, right? They're just at the top level of the query engine, right? But you can also you'll notice that when you do a query, right? When you do a query, the results that comes back from the database, they look remarkably similar to what a table looks like, right? When you do a query. And well, obviously this is a table, right? That is the content of the table for the blogs. Yes. But if you do a query, and you put a where clause where it says that the topic is equal to cars, and then you run that, what comes back is awfully similar to a table. It looks just like a table. In fact, it's not a table, right? It's just a whole bunch of records, right, that came back filtered by a particular predicate, right? This does not constitute a table. I mean, these three records are in a table, but the result set itself is a subset view or screen or results of having retrieved those records that meet a particular criteria. Well, it turns out that this over here, right? This over here can be used as this output of this query can be used as an input, right, to other queries. Okay, so for instance, you might grab this and then say, okay, fine. Now give me everything from, right? And you can now embed this query in there, and then treat it as if it were a table. You can even give it a name, right? So it's in parentheses, within parentheses. See. So what we're saying is that the output of this query is going to be treated as if it were a table. So you can say the name of a variable t, okay, and then you can use t as if it were a table, just like over here we said from, and then the table blogs. Just like over here we're saying from and an actual table. Here, right? This is my fake table. Okay, my fake table. And then I can use my fake table and say, well, my fake table. So what's in my fake table? Well, in my fake table, I have all these fields, all of them, right? I have topics, blah, 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 name, create, update, user, right? I could say, well, where the user, right, is equal to 6. Right, and then I can run this, and then this will filter even further. So out of these 3, so this comes back with 3 records. But if that's the input to this other query, of which I am filtering even further, where this has a field user, I want it equal to 6, then I will filter and only get these 2. Let's see. Let's run that. There we go. So now we have a subset. So what you could do is you could repeat this over and over, right? If you have a very complex question and query, right, you can break it up into smaller queries, right, that you can then take the output of one of them and be then the input of the next, okay? Where you are adding more where clauses, as you make the, add more restrictions so that it narrows down to exactly what you want. Okay. Let's see. Do we need to include the backticks where every time? No, you don't. Yeah. In fact, I didn't use the backticks at all here. Or do you mean so the question is, do we need to use the backticks every time? Or are they not necessary? So yeah, no, they're not necessary. So for instance, first of all, the name of the database is not necessary, right? It's implied here because it's a constant, right? But oftentimes you'll see backticks for this like that. Those are not necessary. They are necessary if the table has weird characters, right? Like for instance, you can create a virtual table, right? By maybe adding spaces or adding something like that, right? And then you would need to put the backticks in there. Could you set a variable equal to the first query? So something like new table selected. We'll learn how to do that. It's not exactly the way we've been doing it in the slides. The slides somewhat imply that you can assign the value of this to a variable and then use it as a variable down here. It's not quite like that. It's almost like that, but not quite. And we'll see that how to do that when we get to views, right? We'll see how to do that in views in a minute. So yes, almost. Closed but no cigar. Okay, so let's talk about subqueries. So there it is. So a nested query, or called a subquery, is a query within a query. Okay, another popular way of calling subqueries are views, right? Inline views. Okay, but that's only if they are used in the from clause, right? But you can use you can use subqueries anywhere. You can use them in the where clause, in the from clause, or the select clause. So let's look at each one of them. Let's look at using nested queries, right, inside of the where clause. Right. So here it is. Here's your where. Here's your select. Here's your from, and here's your where. Okay. Now the where. Notice that there is an embedded select statement. Okay. Now, there are some restrictions of what you can put here. Okay, one of the restrictions is that whatever the subquery is in the where clause, right, it needs to return either, right, a single value or a set of or an array or a collection of single values. So it cannot return records. It cannot return rows, right? It needs to return either a single value or an array of values, but it cannot be records, right? In the from clause, yes, you can return things that look like tables, which are a set of records. Okay, so the from clause, your embedded select statements cannot return a single value or an array of values, right? It needs to return an array of records. Whereas the embedded query here needs to be something that evaluates to a single value or an array of values. Like for instance, this in, see this in over here? Well, the in expects the right-hand side to be an array of values from which I can compare myself, right? So that I can say, is field 1 in the array that this returns, okay? Right, so some limitations and considerations on where you can use these in the where clause, right? So for instance, here's an example of where you would want to use the where clause, the inline view in the where clause, right? So for instance, imagine you had a query where you want the student details where the first name is in Alice, Bob, and Charlie, right? So I want the student details only for any one of these 3 children, Alice, Bob, and Charlie. Okay, well, somebody might say, well, why Alice, Bob, and Charlie, right? What if Charlie graduates and they're no longer here? You need to come back and fix this query, right? Because some of these students might have gone away. Right? Wouldn't it be better if you tell me what is the criteria by which you came up with Alice, Bob, and Charlie? You know, why those 3? Well, we can automate that, and so we can come up with a criteria and say, oh, it's not just Alice, Bob, and Charlie. Actually, it's just the first name of the students whose subject is science. Ah, okay. So I want the student details of all the students that are in the science subject. Okay. And so I can now automate this, and I don't have to hard code Alice, Bob, and Charlie anymore, right? I know what the criteria is, and it's generic like that. So notice that I am retrieving a single field, and this is, it says, well, I want the first name of all my students in the science subject. So this could come back with a list of 3, 10, 20 students, but only the first name. Okay, so it would be wrong for me to say first name, last name, right? That would be wrong. That would be a syntax error. So I'm going to strike through. Okay, that's a no-no, right? It has to be only one field, because the outer in statement, right, is expecting a comparison against an array of multiple values, not multiple fields, multiple values. Okay, so you got to be careful. All right, so let's look at a couple examples here. We have, you know, a table that contains statistical information about all sorts of countries, you know, going from Afghanistan, you know, all the way through the Z's, the A's, the B's, and the Z's, right? And some information about their region, their area, their population, their GDP, blah blah blah. So for instance, say you want to ask, you know, what are the countries with a population larger than Russia? So we need to learn how to break up this question, right? It says list the countries with populations larger than Russia. So that means that I need to calculate a list of countries, right? And whose population, and then larger than Russia. That means that somehow I need to first calculate what is the population of Russia, first of all, right? Once I've calculated the population of Russia, then I can say, well, now I can compare the populations of each country compared, you know, I want to compare that population against the population of Russia, right? Also notice that this select statement right here, notice, right? This is calculating the population of Russia. Now, notice that it's calculating one single value, a single population value, not an array of values, right? Like we did on the in. Here, we're calculating an array of many students' first names, right, that are in science. Whereas over here, this where clause is returning exactly one value. And notice this is very important, because look at the operator. The operator is the greater than operator. If it's greater than, then it means that I want to compare a single value against a single value, right? So it would be wrong for this to come back with multiple values, right? It needs to come back with a single value that I can compare with the population. Okay. Okay, great. So you can also use subqueries in the from clause, right? So in the from clause, this is one of the more common ways of using subqueries, right? It's putting the nested select statement, right, inside a from clause, and then you give it a name, you give it an alias, and then once you give it an alias, you can treat it as if it were an actual table, right? So this is a table now that has fields, supplier ID and total amount, right? Those are the fields of this table, right? Because that's what you're calculating in the select statement. Yes. So that means that this subquery, you can treat it now like a table, and then you can access from that pseudo table, right? Or a view, we call it an inline view. You can use all the properties, right? All the fields for which you've declared inside of your query. So you can, you know, definitely access the supplier ID, because that's what it is, right? You've declared that field in the subquery. Okay, and then you can compare it against other tables, other fields in other tables, like supplier's ID. Okay, let's see. What is the purpose of the as keyword? Right. So this keyword here, as keyword, right? What it does is that, so this field has a very well defined name for that field, right? It's called supplier ID, correct? Whereas this field, notice that it's a calculated field because it's an average, right? I'm sorry, we're adding up all the amounts in an order, right? So one might ask, okay, fine. If supplier ID is the name of the first column, what is the name of that second column? Okay, and the operating and the name is going to be given by your as keyword here, where you say, I want the name of the column to be total amount. Okay. Now, if you leave out the as, it would still work, right? This would still work. It was still calculated, but it would choose the database would choose for you a name for that field based on the operation and the name of the original field. So that name might be useful to you, might not be useful to you. Okay, it might be some weird name like sum orders amount. It might be a weird order name of the field. So instead, you can override that and rename that column and give it an actual name. Okay. All right. So here's another example where we are using the subquery. So we looked at the subquery in the where clause. We use the select query in the from clause. And now let's look at generating a subquery in the select clause. All right. So again, where, from, and select. So in the select, okay, you'll notice that the select has to generate, right? Remember in the where clause, the subquery needs to be a single value or an array of values. Yeah. In the from clause, it has to be records, right? It needs to be multiple records in multiple rows so that it can be treated as if it were a table. In the select statement, exclusively needs to come back with a single value. Right. So here's a select clause, right? That is it's grabbing this table, right? Renaming it to calls, right? And then doing some filtering of some columns and whatnot. Yes. And then notice that what we're doing here is that we're counting, right? We're counting, meaning everything's going to be, we're making sure that all those values, right, are going to be aggregated into a single value, right? So this select statement, we need to guarantee that whatever that evaluates to a single value, just like table owner evaluates to a single value, table name, right, evaluates to a single value. This one too needs to evaluate, right, to a single value. Plus, we're adding the as here, right, keyword, so that because the name of this field, we know it's going to be owner. The name of this field is going to be table name. But if you have this big select statement, what the heck is going to be the name of that field, right? It's just some weird select count, blah, blah, whatever. So we can override and say that's the name that we want for our brand new field that we're calculating. Okay. All right, let's talk about union. So union, like the name suggests, right? It's going to grab the output of two queries, okay? And then so here's a select statement that returns like 20 records, and here you have another select statement that returns 30 records, right? And I want to like concatenate them. I want to splice them together so that I can treat it as if it were one single thing, right? Now there's some challenges on implementing that, right? If you come up with the set of employees, right, in my company, and then you the name of the courses that I'm teaching. Now, can I put that in the same set, right? It doesn't seem like it, right? I mean, you're going to combine pears with bananas, right? They have nothing to do with it. They don't even belong in the same universe, right? So this only makes sense, right, if the values of both queries are somewhat compatible with one another, right? And so you have to make sure, right, that the concatenation of these two values makes sense. right? One of the things is that if you have records here, right, and your select statement comes back with two fields, and then you have another select statement that comes back with three fields. Well, how are you going to paste them together? Because this one has two and this has three. Are you going to put the first column under the second column over here? I mean, how are you going to match them, right? Also, the data types of the fields in one of the select statements needs to match the data types of the other field. I mean, you're not going to concatenate things that are integer, columns that are integer, with columns that are string, right? They would not fit in the same result set. That makes no sense, right? So you need to make sure that you need to massage some of this information, perhaps, to make them in the same result set, right? So let's talk about that. So for one thing, the name of the fields, right? So here's an example of two tables. One is I have employees in Canada and I have employees in the United States, right? And in the employees Canada table, I have fields EID, and you have the name of the actual employee in a field called ename, right? But for some reason, right, in the USA employees, I have similar information, right? Same thing, the names of them are employees, but my field is called emp name. Okay. Well, that's going to be a problem, right? Because if I want to put them underneath each other, well, how is even though we know us with our natural intelligence that the data types of the emp name and the data types of ename are the same data type. Also, we logically understand that these are equivalent to each other, right? But the database doesn't know that, right? It doesn't know that this column is logically the same as this other column. We need to be able to be explicit about it, right? Computers are still stupid, but not for long, right? So we're going to make sure that we explain everything. So how do we do the union of these two things? Like, for instance, if I extract the name of the employees in the Canada data table, but then I extract the employees from the USA table, then to make the union, I'm going to put this here. Oops. Like that, right? To make the union for this to work, I mean, we know this is the same data type, right? So we don't have to do anything. But for the result set to know that these are going to be in the same resulting column, notice what I'm going to do is that I'm going to rename, right, the column in the USA table, emp name. I'm going to rename it to ename, right? So that now, right, the database is okay. I have two fields that have the same name of both result sets. I can't put them one underneath the other. Okay. Okay. And so another thing to consider. Now, if these were of different data types, this would have not worked, right? It would have said, you have a type mismatch between the columns that you're trying to unite, right? Also, if the names don't match, you would not be united. Okay, but one thing that I want to point out is that there seem to be a particular employee that seems to work on both offices, right? And maybe they work half of the year in Canada and half of the year in USA, right? So there are duplicates. If you do the join, Dole Stephen would appear twice. Okay, but by default, union removes any duplicates. Right. So you would not get Dole Stephen more than once, unless you want to, right? You can override the default behavior. Right? You can override the default behavior by adding the keyword all. Okay, union all right? That would return all the records, right? All the values, even if they are duplicates of each other. Okay. There we go. And we can make this a little bigger. All right, a couple more things. There's an order by. So order by is an operation that allows you to, like the name suggests, sort the result set in a specific ascending or descending order. Okay, and now this does not reorder the content, right? The records in the original table stay the same, right? This does not physically move any records up and down. Instead, again, it's only when you extract the data from the database, right? And before showing it to the user, you can ask the engine, your database, to reorder the result set so that certain columns are in ascending or descending order, right? Again, this is only for visualization, right? I want to see the data sorted by last name, right? Sorted by city, sorted by salary, whatever, right? And so the keyword is you say ordered by, just ordered by. Actually, there's a space here. So order by. So order space by. And then you can order by multiple columns, right? So you can say order by column 1, comma, column 2, comma, column 3, and so on and so forth, right? The most common way is that you sort by one column. That's the most common way to do it. But you can also sort in multiple columns where the additional columns you're sorting, within the context of the first column, right? So once the first column is sorted, the second column, right, is then sorted within the first column, right? You can also say whether you want ascending, which is the default is it's ascending, or descending, and you can say that for every single column. You can say column 1 ascending, column 2, comma, column 2 descending, comma, column 3 ascending. Okay, or if you leave out ascending, descending, by default it's ascending. Right. So here's an example where we are, we have an initial set of records, Boom, Nielsen, Garcia, Doe, and we order by last name. The original table stays the same, right? The original table doesn't change, right? Only the result set that we get to consume is actually modified. Here's an example on descending. Self-joins. So self-joins, if you remember, self-joins allowed us to do hierarchical records, right? Or data structures that had a root, right? And then you could have like branches off of that root, and then each branch, right, at each node in that branch, you could have additional subset, right? So to create this, right, in the way we captured it in, the way we captured it in class diagrams is that we had a box, right, that represented the class, and then we just, I didn't mean to do that. And then we had a line, right, that allowed us to do a loop, right, in the class diagram. Remember that, where you had like a one to many going off of one side, one, and then to many. And then the way we would implement that, right, is that we would have a regular primary key, right, like anything else, but then you would have a foreign key that foreign key would refer to the same table, the primary key in the same table. Okay, and this would allow you to create hierarchical data structures, right, where you would have the root would have the parent pointing to null, meaning I don't have any parent, I am at the top, right, of the pyramid, whereas everybody else is pointing either at me right? Or pointing at my siblings, and then my grandchildren are pointing to I'm sorry, no, not my siblings, my children, right? So I'm at the top as a parent. I have my children, and then they have their children, and then they have children's children, and so on and so forth, right? Each one pointing to the parent one. So here's an example of a category, right? So a category is a very good example where you might have a category and then a subcategory and then a subcategory, right? And it will look something like this. For instance, the top level category, I can insert data, and we haven't looked at insert. We'll start looking at insert next week. But like the keyword says, right? You're inserting into a table. I'm inserting into the categories table, and I'm inserting the top, right? This is a top category of products, right? And it has no parent. So my parent is null, right? So I don't have any parent. But then notice that this is auto incremented. This is auto incremented, right? That means the category, when I insert, it automatically generates this record with notice that I'm not passing a primary key. I'm passing null for my primary key. It means that it's going to get auto incremented. So it gets 1, right? The ID of 1. So the other two, electrical and movies, those are subcategories of top. So because I know when I inserted top, it got an ID of 1. These two are saying that the parent is 1 here. See that? 1, which is pointing to this record that I just created earlier. Now these create IDs 2 and 3, right? Because this is 1, then these are 2 and 3. So electrical movie, electrical appliances is 2, and movies is 3. So 1, 2, and 3. So here we have PICs, or maybe PCs are under the electronics category. So it's saying that the parent is 2 because this, when I inserted this, it added a record of ID 2. Whereas for movies, right, notice that I have DVDs and Blu-rays, okay, are under the movies category, right? So this is 1, 2, 3. So they're pointing to number 3 down here, okay? Okay, so once you have that, you can then retrieve data. You can retrieve data and say, well, why don't you give me a list of all your parents and movies and whatnot, right? So for instance, I can say, take the two, when basically I want to say, give me a, if I ask you for PCs or if I ask you for movies, well, tell me what category are you in, right? What category are you in? Well, that means that the name of my child, right, and the name of my parent are actually in the same table. So how am I going to get that, right? But where one is going to be one, if I had 2 tables, that makes sense, right? I can join the 2 tables. And then retrieve the parent name or the child name from each one of the tables, and then I can give you the result. But here, they both exist in the same table, right? So here's an example that I'm joining the same table with itself, right? Notice that the 2 tables are called as categories and categories, right? So the same category table is being used twice. But in one of them, I am renaming it as a child, and the other one I'm renaming it as a parent, right? Because I know that the child has a foreign key that might be pointing to a parent, right? That it's a record in the same table, right? Okay, so which ones do I want? I only want the ones where the child's parent ID, right, the foreign key, is pointing to the primary key of some record in the same table. And in this case, I want where the parent name is movies. So this might be returning to me all the CDs, right? All the DVDs and Blu-rays for the category movies. Okay, one last thing, portable nums. So let's talk about portable nums, portable enums. So enumerations as we've seen before, right? Basically allows you to establish a set of approved values for some other field, right? Like for instance, right, this is something that you would that you would find in a UML class diagram, right, where you have a class movie, and it has a field called genre, and genre. I mean, we could put here a string. You could say it's a string, and then you're allowed to put any genre you want. Okay, but that's very dangerous, right? Because that would allow me to type anything I want for genre, right? So a much better design is to limit, right, or validate whether the genre that is being added here is valid. Okay, a string is too generic, right? It's not explicit enough. So we can generate our own data type by using a class. Okay, which we can say that this variable genre is of type genre, which is right here. But this is not a class at all. It's not a class. We're saying that this is an enumeration. See that we're using a stereotype. We're saying that what we're going to paste in here, the values that we're going to paste in here, these are not properties. Right? These are not attributes of some class genre. Instead, these are the only possible values, right, for that data type genre. Meaning we are limiting the possible values of the genre variable with this genre enumerator type. So how do we implement this? Right? And we want to implement it. We want to implement it the same way across multiple vendors. So whether I'm using Oracle, whether I'm using MySQL Server, or SQL Server, or Postgres, or any other database, right? How do I implement it in such a way that it works, the solution works for all of them, okay? And that's what we mean by portable. Portable means that even if you implement it in Oracle, you can take that code and it'll work just the same if you employ it in MySQL or SQL Server or Postgres, right? Now, MySQL has a keyword called enum, right? And you could absolutely use enum, right, for this purpose, right? I can say, here are the sizes, and the name of the sizes can only be either string small, medium, or large. So this absolutely implements our understanding of enumerations. Yes, but the problem is that enum is a reserved keyword of MySQL, but it's not of other databases, right? So if you implement it this way, you're going to be tied to MySQL, right? If you want to take this code elsewhere to another vendor because your organization is now using Microsoft SQL Server, then you're going to have to re-implement this. Okay, so ideally we would not have to re-implement any of this. The code exactly as is verbatim and move it over to another database, right? Which this is not going to allow us to do. So how do we do that? How do we implement portable enums, right? So the way we're going to implement it is that you're going to create a table. You're going to create a table where you're going to keep track of all the valid values in there, right? And you're going to declare it as a primary key, meaning it cannot repeat, okay? And then you're going to insert into that table, right, all your valid values, right, like comedy, drama, horror. So we're introducing into the genre, inserting into the genre table, into the field name, the values comedy, drama, and horror. Notice that they are declared as primary key. It cannot be repeated, and it can participate in a foreign key, primary key relationship. Now, on the other side, where we might have a movie that declares a field of type genre, the way that is implemented is a table where genre, your field genre, would be of the same type as the primary key of where the genre is declared. And then we would add a constraint saying that this genre varchar is referencing, it's a foreign key, okay, to the genre table declared earlier, right? And this way, this genre, because it has to be a foreign key, it cannot have any values other than the values for which you chose, the values that you had inserted into the name varchar, right, of the genre. So in that way, right, it's behaving identically functionally is behaving the same way as the enumerated data type. Okay, but this implementation is portable. You can take it with you, right, and implement it elsewhere. Okay, excellent. All right, let's talk about views. Right, so somebody was asking earlier, hey, those subviews, those subqueries, right? Could we assign that, right, maybe to an intermediate variable, and then use that variable, as a table in another query? And I mean, we've been using that syntax in our lectures, right? Even though it's not official, it's a very unofficial language, right? So it turns out that you can do something similar to that, almost as easy as declaring a variable. Okay, so what you do is that we use what is called views. Right? Views is the capability of assigning a select statement to a keyword. Right? So here's our select statement. Whatever select statement you want, it could be as complex as you want. Okay, and then you can give it a name. You can give it a name so that you can reuse this over and over, right? So that you say the keyword is you create view, the name of your view, and then as being the value of the select statement, right? That retrieves the data. Okay, right? So this is almost what we've been doing, right? Where we're saying, view name equal, and then the select statement, right? And it's not like it's storing the value in the view. It's not like it's creating a variable and holding the values in that view. This is just delegating, or it's deferring the execution of the select statement to some later time, right? Every time you refer to the view, okay, it will run the select statement, right, and go fetch the latest values and then bind it to your view name here. Okay, so let's take a look at an example. So imagine, we create here a current product list. So current product list, right? Also notice that in our view we decided to put spaces in there, right? It's totally fine, but notice that to do that we had to put the quotes in between. See that? So the quotes on either side, right? So it's current product list, even though it has spaces, that's totally fine. As long as you put quotations on either side. So create a variable called current product list that is going to hold the value of this select statement whenever it runs. So what does the select statement do? Well, it's current product. That means that this should be false, right? Discontinued should be false, right? So basically, return the product ID and the product name from the products table where discontinued is false. Okay. Now that you've declared that and assigned this query to this variable, you can use that variable like you would expect. You can use it later in another query, right? And treat it as if it were a table, right? So it's like the output of one is the input to the other. Right? So basically, it's the same functionality as we have been describing. Okay. Here's another one. And wherever you think that you can put a table, or most places where you think you can put a table, you can also put a view, right? So for instance, here's another example where we are creating a view. We're creating a view, and that view has a nested query. See that, right? So you're having a select statement, right, that is being used to declare a view, and that select statement contains a subquery, right? This is just to show, how complex and sophisticated this could get, right? As things, outputs of things become inputs of others. Okay. Or if you had initially declared a view, say you had declared a view, well, you can declare another view in terms of another view. Right? So this is insane, right? I mean, this is somebody had to create a view. We gave it a name, and then we're using it here as if it were a table to create another view. and then that view is being used in another select statement. So basically, you can create a whole hierarchy of views within views within views within views. I mean, and that they would be resolved at runtime, right? When you ask for this, right? When you ask for this, right? This would have to run. So that means it would run this select statement, right? For that category for sale. And this select statement is going to cause this one to run, the red one. And the red one, right, would cause that select statement to run, and so on and so forth, right? So you can create a hierarchy of queries where the bottom ones feed the top of ones, right? The feeding goes from bottom up. So yeah, this is just to point out that we've been using this syntax almost this syntax for a while now, right? We've been using this syntax instead. We've said Q96 is equal to the select statement, right? Now, obviously, this syntax is it's not valid syntax. It was our own syntax, but it was a shorthand for creating a view, Q66 as, and then the name of the query. Okay, so yeah, so we've been using it, but obviously not using the formal syntax. And it says, what isn't that inefficient? What's inefficient? Well, let's talk about efficiency, actually. Yes, so unlike tables, right? Tables contain actual data, right? And when you do a query, when you do a view, the view executes every time you refer to it. Okay, it's not like the data is there and I just have to fetch it, but I actually have to calculate it, right? I have to fetch it, I have to massage it, and then come up with the results, right? So views is only a how do you say, a convenient way of reusing things that are nested. Okay, it's views are almost just like functions, right? In a functional programming language. I mean, you could put everything in the main function, but as you look at algorithms that you say, oh, this algorithm is very useful, instead of copying that algorithm multiple times, why don't I grab that algorithm and put it in a separate function, and I give it a name? Yes, and then now my main function becomes much smaller in terms of a whole bunch of other functions. And those functions themselves could be written in terms of other functions. Yes? Okay. Obviously, when you call a function, it always executes, right? It's not like it remembers anything. It reruns from scratch. In that sense, it's the same way here. Whenever you refer to a view, it needs to re-execute and recalculate whatever it had initially, right? So this is not any more inefficient than using functional programming of saying, well, I'm going to call a function. Isn't calling a function more expensive because I have to create a stack, right? I have to create a whole bunch of dereferencing, blah blah blah, right? And then I have to jump to another address and then come back and throw away the stack. Yes, but obviously, the beauty of the function is that it allows you to create very complex applications in terms of smaller, more understandable algorithms that are reusable. Same thing here. Basically, you are giving a reusable select statement that you want to use over and over and over again. Instead of copying and pasting it, you're giving it a name so that you can then refer to it by name, and it recalculates whatever that query is. Right now, there are techniques where a view might be made or converted into an actual table. Okay, and we'll talk about that. We'll talk about where a view might want to be converted into an actual table, right? Besides manually inserting values into tables, how is data usually brought into your database? Oftentimes, it's either generated by some automated algorithm or some or folks doing data entry, and users filling out forms when they order something online, or the somebody delivering a package to your to your door, and when they do bleep right on the product when it's delivered, that is sent to some kind of server that does an insert or an update in a database, right? So a lot of it is all automated, right? And it's logging, right, the process of the business, right? And it's which then can be queried, can be aggregated at the end of a quarter, at the end of a year, right, where you can extract all sorts of statistics and performance and all sorts of reports, right, on the business. So every time you sell something at a store, right, or at the cash register, right, there's the updates are coming in and out, right? And so a lot of it happens automatically, right? So and we and as software engineers write all the software to automate this as much as possible, right, and eliminate any manual entry, right? We still have data, manual data entry, but most of this is being replaced by artificial intelligence that can read forms, that will auto insert all sorts of things into the data. Many times we do data dump, and then we do imports of large amounts of data that sometimes need to be massaged and cleaned, because there might be a lot of bad data, and convert it into useful data. Yeah, so we're using queries. So just like over here, we named a query, right? Where we named a query, and then the equivalent way of implementing it would be using the create view. Once you create the view, using the syntax, you can then use it pretty much as if it were a table, pretty much the way we've been doing and using a table, right? And again, it's the equivalent of expanding that query into its equivalent embedded syntax, right? It's the equivalent. So other than obviously being a useful way of reusing queries, it also goes back to the conversation we had at the beginning of the semester of providing views being a way of providing what we call external schemas, right? So if you remember at the beginning of the semester, we talked about that databases today, modern databases, provide different levels of abstraction of how the data is being represented, right? Obviously, when we talk about tables and rows, right, and records, that's all an abstraction, right? It's, if you look at the file system, there are no tables, right? There are no records, right? There are no rows and columns and schemas, right? That's all a layer of abstraction that we have invented, right, by creating databases, right? That allows us to conveniently talk and interact with large amounts of data. Okay, so we have the conceptual interpretation on how we are going to store data. We have the physical schema, right, on how is it that this is going to be all the bits and bytes of how it's going to be stored in the file system. But then we have what it's called external schema. So external schema is an even higher level of abstraction. Okay, so so up to this point we've been talking about kind of like the conceptual schema, right, on how is it that we think about the data conceptually. We think about it in terms of tables, and we spent a lot of time deciding what is the structure of our conceptual schema, right? Should it be 2 tables, 3 tables, right, 4 tables? Should we split a particular table? Is it maybe not normalized? Is it breaking second, third normal form, right? All these are conceptual things, yes, right? Because we're trying to make sure that there's no repetition, there's no redundancy, because we don't want any inconsistency. All of this is conceptual. Tables don't actually exist, right? They are converted into zeros and ones, at some point, right? But tables is a nice abstraction layer that allows us to think about it in an easy way. Yes. And then obviously, if you go to object orientation, we have other concepts such as classes and inheritance, right? And interfaces and methods. That's another layer of abstraction on how to think about data. Okay. So the point I'm making here is that beyond conceptual schema, there is what we call external schemas as well. So in conceptual schemas, we saw that we made an effort at removing redundancy and making sure that our tables is the way we structured our tables is the best way, right? By making a class diagram and converting it into a table, blah, 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 right? And no redundancy. It meets first normal form, second normal form, third normal form. And this is the best conceptual set of relational database that we come up with. Yes? But somebody might say, oh, you know what? Why did you break up this nice table into 2 or 3 tables? It's so inconvenient, right? If I want to ask and find out, students that graduated in computer science a particular semester in this enrollment and were a transfer student from another college, oh man, I have to join this table with that other table, with that other table, with that other table, create this, complex query. And it would have been nice if you would have left it all in a single table, right? So one thing is convenience of how I want to retrieve the data. And the other one is making sure that the data is sound and it has no inconsistency, no redundancy. So oftentimes the goals of these two, are not consistent, right? External schemas are for the end user, right? Our customers, our partners, right? Our clients, our maybe it's the registrar's office, the dean's office, and they want to use the database, but they might find your conceptual schema way too normalized. Okay, says, wow, why do we have so many tables? And we as data engineers, we would explain, well, I wanted to make sure that it was normalized, and I split it into these number tables, and that's the best design that we can come up with. But from external schemas, they say, oh, you know what I wish? I wish these 2 or 3 or 4 tables were actually one thing, right? That would make my day much easier. I like to have it as a report, okay? Everything in one single place, not having to go fetch things here and there. Well, it turns out that views are a perfect solution for this, right? Instead of creating a denormalized table that has a lot of redundancy, that has a lot of stuff in it, right, and could have inconsistency, instead of breaking first normal form and second and third normal form, just because of the convenience of some clients, right? Instead of doing that, we could create a view that joins 2, 3, 4 tables all into one single place and generates for these folks, right, a convenient way of looking at the data without actually breaking our design. Okay, so for instance, we might have 2 tables, right? We might have as the dean's office might want, right? They might have wished for a table called student info or student courses, right? Which brings in data from the courses table and the students table and puts it in one single place, right? Or student info, which grabs information from sections, from enrollments, right? From students, right? From departments, and puts it all in one single place. Okay, so the dean's office would rather have that instead of having everything spread out on a whole bunch of different places. So views is perfect for implementing these kinds of things, right? You create for instance, you create a view called student courses, right? That that does a select statement that joins three tables, enrollment, section, and course, right? Joins them together into one single place, and then we create a view. And now we can create maybe a user interface in front of this, right? So that the dean's office or the registrar's office can easily consume this data in a much more convenient way. And this is what we mean by external schemas, right? A schema that sits on top of the actual schema, right? It's like a virtual schema, right? That it's not really how we broke out the database, right? But it's convenient for others, right? But it's built on top of the actual schema, right, of actual tables that need to be joined to create the other alternative schema. Make sense? Okay, great. All right, so also remember we said that views could be treated as if they were tables, right? And that's almost true. You know, almost everywhere you can use a table, you can also use a view, all right? But not exactly everywhere. Okay, let's revisit that idea. Okay, let's revisit that idea. So if the view, right? I mean, ideally views are indistinguishable from tables. Okay, but updating views, right? So because imagine for reading purposes, for extracting data, for collecting data from views, yes, they are indistinguishable from tables. Yes. But for other operations, like inserting into a view or updating a view, right, or something that looks like a record, right, like a row that comes back from a view, well, that row, it could be that a field in that row is actually an aggregated value, right? One value in there could be the sum of a whole bunch of other records. So what would it mean to update that value, right? Which is an aggregation of a whole bunch of other values. Does it mean that, if you add it, if it was an addition or an average, and you can update that value, and the original values were, 10 records had to be averaged for that one field, what would it mean to update that field? It makes no sense, right? So if things are updatable in a view, you can update records or values in a view only if that value is uniquely corresponds to the underlying table, right? So if you have a record, right, and you have a field in that record, and you can map that record to the actual record from the original table where it came from, okay, if it's uniquely identifiable and says, yes, this record in the view, which is not really a record, right, it came from this record in the table, and if you're updating this field in that record and it's uniquely tied to a record and a field, right, then it's okay, you can update it. Okay, so for instance, a single table with a single field, sure, that can be done, right? Because imagine you had something like this, right? Imagine you had this view here that is selecting data from two tables: the student and the department table. Yes. So some fields, the student name here is taken from the student table, and the department name is taken from the department table. Yes, two different tables, and they're joined. Perfect. What would it mean for you to delete? Say you want to delete this record here. What does that mean? How does that translate if you want to delete that record? Does it mean that you delete the record Joe? Does it mean you remove the department? Is that what it means? Okay. Maybe the most intuitive way to interpret that is that you want to delete the student record. Maybe that's what you mean. But it could also be interpreted that I want to delete the math department. Does that make sense, that I want to delete a whole department? Maybe not. Or it might mean that it could be interpreted as, if you want to delete this, maybe you mean that Sue is no longer in the math department, right? So you're not really removing any of the two records, but you are making the foreign key of Sue no longer point to the primary key of math. So it's not clear how should this be interpreted. right? And because it's not clear, you can't do that, right? Views don't allow you to delete records, right, or records in a view from where the fields have come from two different tables. So if it's a single table, it's okay. But if it comes from two tables, then it's ambiguous. What is it you want to do, right? How about inserting? How about into that same view, say you want to insert into that view. How should that be interpreted? What does that even mean if we want to insert, say Joe is in art, right? And Sue's in math and Alice is in computer science. And you want to insert Joe drama into that view. What does that even mean? Does that mean that Joe is no longer in art and instead the foreign key of Joe should now point to drama? Is that what it means, right? Or does it mean that Joe is now in both art and they are also in drama, if that's even possible, right? Right? If this is just if it's implemented where you only have the foreign key, the student has a single foreign key to the department, then you could implement this, but you could not implement this, right? You need to have like a mapping table that allows Joe to be in multiple departments, right? If it's going to be in drama and in art, right? So again, this is not intuitive. It's ambiguous. We don't know what it's meant. So the only solutions that is left is for us to do it programmatically, right? We're gonna introduce next week. We're gonna introduce how do you do this programmatically, right? When you don't know what to do and it's not explicit and it's ambiguous, right? We need to be able to add some programming capabilities and say, no, this is exactly what I mean, right? This is what I want you to do, right? We have detected that you want to insert into a table, and this is exactly how you're going to implement it. Okay. All right. Let's see. Any questions? Group by. Let's talk about group by. And we got 5 minutes to get started. Any questions before we get started? All right, let's talk about group by. So group by, right? So remember, group by was a mechanism that allows us to look at a whole bunch of records, right? And as you're iterating over the records, we wanted to group by one of the fields. We want to say, well, are the values in that field, do they repeat, right? Are there values where some a whole bunch of people liked this tweet? Okay, is there a way that we can group them, right? And can we add them together or average them out, right? So group by allows you to do that. It allows you to say, okay, let's look at 100,000 records, and we see that a particular field repeats 1,000 times here, 500 times over there, 200 times, 10,000 times, right? And if you can group by that value and says, okay, well, these 1,000 records, right, where this field is the same, I want to collapse it and want to combine all those 10,000 records into one single result, okay? And so that's what group by allows you to do is identify sets of records that are somehow related to one another because they fall inside of a particular range, okay? So the way you do that is by adding the group by keyword, group by, okay, where group by has no underscore here. Okay, group by like that. Okay. And you can provide here the column names, so it can be plural, many column names that you want to group by, right? And so it says, which again, it means really that it's going to iterate over all the records, looking for that in that field, looking for repetitions. And whenever it sees a repetition, it puts them in a separate bucket, right? So for that column name, if it'll put in the bucket all the ones where the column names, the values are 10, and the other one where the column is 20, and then another bucket different if the values are 30, right? And then it says, well, what do you want to do with each bucket, how do you want to aggregate it? And so it allows us to give here an aggregation function of what to do with all those records that now fall in different buckets. Right? How do you want to aggregate, right? And you can combine the other fields, you can combine them, right, into a single value. So here's an example of having a table that has customers, orders, order dates, and order IDs. And you'll notice that in the customer column, we have Alice repeating 3 times, we have Charlie repeating 2 times, and we have Bob just 1. So if you group this table by customer, you'll end up with 3 groups: 1 for Alice, 1 for Charlie, and a 3rd for Bob. Okay, and which means that in those same buckets, so in the Alice bucket, you're going to have 1,000, 700, and 300 in one bucket, and you're going to have 1,600 and 100 in the Charlie bucket, and you're going to have 2,000 in the Bob bucket, right? So the question is, well, what do you want to do with those values? What do you want to do with these 3 values that are in the Alice bucket? What do you want to do with these 2 values that are in the Charlie bucket? Well, one of the things that you can do is that you can aggregate them. You can put an aggregation function and say, oh, well, what I want to do is I want to add up all these 3 values that are in the Alice bucket, and that's going to give me the single value of that for that particular bucket, right? So I'm going to do the sum of the order prices. That's the aggregation function of the order prices. So in the Alice bucket, I'm going to get 2,000. In the Charlie bucket, I'm going to get 1,700. And in the Bob bucket, I'm just going to get 2,000. That makes sense? All right, I'm going to leave it here. We'll pick this up on Tuesday, all right, next week, and we'll finish up group by. All right? All right, everyone. Thank you.
Thank you. Thanks.
Bye-bye.
Thank you.
Thank you.
Bye. Take care.